Question 3. Two identical spheres are suspended by light insulating wires of equal length from a single point. When both spheres are given the same charge Q, they repel as shown in the diagram below. Draw a free body force diagram for the sphere on the left. Not left much room here. So it's got three forces acting on it. We use three different colours. Firstly, acting downwards, it's weight. Secondly, obviously they can come in any order, we've got a tension force from the string. To help ourselves in a minute, we might label the angle theta, just so that we remember where it is. And lastly, it's got an electrostatic repulsion force. This is going to be horizontal. This is the force caused by electrostatic repulsion from the other ball. The length of each string is 0.25 meters, and the angle theta formed between each string and the vertical is 10 degrees. Find the distance between the balls. So this is a bit of trigonometry, isn't it? We've got an angle of 10 degrees, a length here which is 0.25 meters, and this is obviously half of the distance between the balls. So if I find x, the answer to this question is actually going to be 2x. So we can see that the sine of 10 degrees should be equal to x over 0.25. So x is equal to 0.25 times the sine of 10. Check you're on degrees before you calculate it. So this is 0.043. So the distance between the balls, which I'm going to call D for the sake of this part, should just be 2 times that, which is, whoops a daisy, what have I done? 0.086 meters. The mass m of each ball is 0.15 kilograms. Find the charge Q on each ball. So when these things are stationary, we know these three forces are going to add up to be equal to 0. We could draw a closed vector triangle over here of the three of them, like this, something like this. Obviously that angle's nowhere near 10 degrees now on my diagram. Or we could look at the vertical horizontal components. I'd prefer to do that. So starting by looking at the horizontal components. In the horizontal direction, we know the electrostatic repulsion Fe should be equal to T, so we're going to resolve T into two components. One that way, one that way. This one is the one away from the angle, so it's T sine theta. This means that T should be equal to the electrostatic force over the sine of theta. The electrostatic force we can get, sorry, we're trying to find the electrostatic force, aren't we? We should have done the other one first, but we can carry on from here. So this is Q squared over 4 pi epsilon naught R squared, or D is what I've written it down as here, isn't it? So let's stick to that notation. D squared times the sine of theta. So that's the size of the tension force in terms of Q. Then if I look at vertical components, which would have made more sense to do first, I know that W is equal to T times the cos of theta. So from this I can get T is equal to W over cos theta, which is 0.15 times 9.81 for the weight, divided by the cos of 10 for the angle. So let's work that out. So that's 1.49 if I write it to 3 significant figures, 1.49 newtons. So then I can put this value of T into my equation at the top. I'm going to get that Q squared is equal to T times 4 pi epsilon naught D squared sine 10. So for Q, I want to take the square root of both sides. So we get 1.49 multiplied by 4 pi multiplied by 8.85 times 10, where are we, times 10 to the minus 12, multiplied by the separation squared, so that's 0.086 squared, multiplied by the sine of 10, which gives me the charge is 2.1 times 10 to the minus 19 coulombs. Sorry, I finished that video. I forgot to square root. So the square root of this, so the coulomb shouldn't be there. It shouldn't be underlined yet. When I take the square root of this value, I get 4.6 times 10 to the minus 7 coulombs, which sounds like a more reasonable value as well when I write it down.